Okay, let's try another example. I was going to look at f of x equal to the sine of x. Both of these were done in the book, but they're good to work through and see done. I think it's helpful. Okay. So I'm going to write sine x as sum. I want to see if it has a Maclaurin series. Sum n equals 0 to infinity of cn x to the n. Let's see if we can figure out what the coefficients are. Let's write sine x as an infinitely long polynomial. All right, so let's see. Well, I know that f at 0 is sine of 0 is 0, right? And so that c0 is 0. What's my derivative? Derivative of sine is cosine. So f prime at 0 is cosine of 0 is 1. And so C1, let me list these over here. C0 is 0. C1 is 1 over 1 factorial. I have to remember to divide by the factorial. In that case, it doesn't matter. Okay. But I don't want to forget that, right? Okay, second derivative. The derivative of cosine is negative sine. So the second derivative at 0 is negative sine 0 is also 0. Okay. So C2 is 0 over 2 factorial, which is 0. The third derivative of negative sine is negative cosine. So the third derivative at 0 is negative cosine 0, which is negative 1. Okay. So C3 will be negative 1 over 3 factorial. Okay. The fourth derivative of negative cosine is positive sine, which takes us back to the original function. The fifth derivative will be cosine, sixth derivative will be negative sine, seventh derivative will be negative cosine, etc. Okay. So the fourth derivative at 0 is 0. The fifth derivative is 1, sixth derivative is 0, seventh derivative is minus 1. So my C4 is going to be 0. C5 is going to be 1 over 5 factorial. Right? This 1 over 5 factorial. C6 will be 0. C7 will be minus 1 over 7 factorial. Right? So all the even coefficients are 0. Only the odd coefficients are non-zero, and they change sign. Right? So let me write some of these out. So I have 1 times x to the first minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the fifth minus 1 over 7 factorial x to the seventh, etc. So I get the odd powers of x. The denominator is the power factorial in alternating sign. How can we write this as one nice compact sum? You have to be a little bit clever on some of these. So let's start with sum n equals 0 to infinity. I want odd powers, so let's do x to the 2n plus 1. Take a number, any integer, multiply by 2 makes it even, add 1 makes it odd. So that gives me all the odds. When in a 0, I start with 1. Then I'm dividing by that power factorial. So 1 factorial in the denominator here, 3 factorial for n equal 1, 5 factorial for n equal 2, 4 plus 1 is 5. Now I need to get the alternating sign in there, so I can do that with a minus 1 to a power. What power? I want to start with a positive. When n is 0, I want it to be positive, so let's just make that an n. When n is 0, I get a 0, positive 1. When n is 1, I get a negative 1, and that gives me the alternating sign. Okay. So there's a Maclaurin series, power series for the sine of x. If you ever want to know what's the sine of 1, and this is important that it's in radian measures, not degree measure, you could add up plug in 1 here, right? 1 minus 1 over 3 factorial plus 1 over 5 factorial minus 1 over 7 factorial. So the alternating sum of 1 over the odd factorials adds up to the sine of 1. Don't know if you ever would have guessed that. Notice that all the powers are odd. Remember that from pre-calc, sine is an odd function. Now we see it in the Maclaurin series here. Right? If I plug negative 1 in for x, I'll get negative sine x. Sine of negative x is negative sine x. We see that with the Maclaurin series. Once I get a formula for sine x, I can now get a formula for cosine, because the derivative of sine is cosine. I'll let you figure out what's the interval of convergence for this. Check it out. Okay. But let's differentiate. So cosine x will be the derivative of this. Sum n equals 0 to infinity of the derivative of negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. Derivative, so I immediately switch the derivative and the sum. So I bring down the power. Two n plus 1, x to the 2n, decrease the power by 1, and then I've got 2n plus 1 factorial. Okay. But this factor, 2n plus 1 factorial, is pull off the first factor, 2n plus 1. The next factor after that is 2n, and then 2n minus 1, 2n minus 2, etc., which is all 2n factorial. So here the 2n plus 1 will cancel with that first factor. So I have here the sum n equals 0 to infinity of negative 1 to the n, x to the 2n over 2n factorial. So let's put that over here. Let's write out some terms. So the cosine of x is the sum n equals 0 to infinity, negative 1 to the n, x to the 2n over 2n factorial. When n is 0, I get 1. 0 factorial is 1. When n is 1, I get minus x squared over 2 factorial. When n is 2, I get plus x to the 4th over 4 factorial, minus x to the 6th over 6 factorial, plus, etc. There's a Maclaurin series for cosine. There's a Maclaurin series for sine. That's 4 factorial there, by the way, okay? All right. So I'll let you play around with finding the radius of convergence and interval of convergence for both of those functions. But that's the idea of Taylor and Maclaurin series. You have a function, it's got to be infinitely differentiable. Compute its derivatives, evaluate those at the center. You can use that to get your coefficients. You can get, then you want to be a little bit clever on how you write the terms of your series. Okay? Extremely powerful. Notice that, well, I'll leave it at that, okay? So I hope this helps. I'll see if I can get these videos up online tonight and see if that helps clarify some of this material. All right, have a good night.